377, but if we have additional information, then EY could be 391 if we get the 6. Okay. And the second example, this is generally the Monty Hall problem. It is named after the original host of popular TV game show, as it is typical of the type of decision making that the guest show sometimes have to make. So a valuable price is randomly hidden behind one of the 3 doors, okay? And you have to guess the correct one. If you choose one door and the host opens another, revealing that there is nothing behind it, then you have 2 options to decide whether to stay on your choice or to change the door, okay? Have you known this problem before? Does anyone know this problem? Maybe you've seen in the movie. So there are 3 doors and there is a price behind one of the doors. So doors number 1, 2, 3. So you let's say you selected the number 1, and the host of the TV show shows okay. It opens door number 2, and there is nothing inside, no price, and he asks you a question: are you going to stick with your first choice, door number 1, or you will have to change and choose door number 3? So what you are going to do? Should you remain with your original guess or change? So there is only one price under the door. If you open the correct one, you got the price. If you don't open the correct one, you got nothing. So let's deal with this problem. So this is like the it is crucial condition, the crucial condition that the host won't open the price door to reveal, okay? He always will open the blank door on every guess. And the situation changes drastically if there is an option of doing so or not. For example, if the strategy of the host was to show you a blank door only when your guess was right, in an attempt to talk you out of a price, then obviously you should never switch. But a great number of people think that you shouldn't switch in any event. Monica, do you know this type of problem, the Monty Hall problem? This is yes. This is about probabilities, and we have to decide whether to switch or to stay on the door. So this is like the Monty Hall paradox. Monty Hall is named by the TV show. So a great number of people think that you shouldn't switch in any event. They reason that since there is always one blank door among the 2 remaining ones, the revelation gives you no information at all, and you may just as well stick with your original choice. And this is incorrect. Under our stated condition, we can apply Bayes' theorem as we did above, and let BI denote the event that the prize is behind door I, and A the observed event that the host opens door 2. We know that precisely one of the events B1 or B3 occurred, and we have to decide whether is more likely. So now the original probabilities are 1/3 for each event. There are 3 doors, 1/3 probabilities. However, the probability of A respectful to B3 is 1, since the prize was behind door 3, and the host had no choice but to open door 2 in order to give you a guess. Without knowing the strategy, the host uses to pick between 2 doors that have nothing behind them. We can only say that the probability of A respectful to B1 is some number P. The new probabilities given the event A are then proportional to P for A1 and 1 for A3. And you know, this is the paradox. Since P cannot be bigger than 1, it is clear that you should switch. As an example, in this case, that the host picks randomly so that P equals 0.5, the probability that the prize behind the door 3 would be 2/3 as opposed to 1/3 for door 1. Okay, let's try to simulate this thing in order for you to get the understanding of what is happening here. Monty Hall paradox. Okay, we have to use the library and install package first. It is from the tidyverse, but let's install packages. Magritter. Install packages Magritter. Okay, library Magritter. Let me make things larger. Alright, so the strategy between 2 choices. The first choice is always switch. Always switch and never switch. There are 2 choices. And let's simulate. We create the function. And this function will have the number of doors, which is 3, and the strategy, the argument strategy, will have these 2 options. So the first one will be always switch. Always switch with this. Okay. So we open the brackets and start. If number of doors less than 3, then the game cannot be played. Okay. Then we create the variable doors inside. This will be the number which will be like this, from 1 to n doors. Price door will be determined as a sample between doors. So we don't know what the price door is, but it will be determined inside the function. And the host opens something different than we have selected. Different between price door and player selected door. First choice. And there will be the sample of n doors minus 2. So this is the... We also need to create the player first choice. Player first choice will be also sample of doors 1. Okay, so we have created the number of doors. Let's say now number of doors is 3, so here is 3. Price door is just one number from 1 or 2 or 3, and we also selected first choice 1, 2 or 3. Host opens different between price door and player choice, and player final choice. Instead of first we get final choice will be the switch strategy. Switch strategy, this one, always switch. Will be difference between doors and player first choice and host opens. Okay, and another one is never switch. It will be the player first choice. This one. Okay. So I guess this is the function. Let's use this function. And now there is the usage of the function with the if-else. If-else player final choice equals to price door equals to price door, then we just apply 1 and we just apply lost. Okay, hold on. and we have to put this if else inside the function. So this is the function. Okay. Okay, do you get the idea what is happening inside? So we just enter number of doors and strategy. Doors will be the sum 1 to 3. Price door some number. Player first choice also some number. Host opens some different. Player final choice will be the different from the first choice, and different from the host opens because we opened. And never switch, we stick to the first choice. And we determine whether we got the price door, whether this final choice equals to the number or not. Okay, let's use the set seat and try to replicate, let's say 1000 times, this function. Play Monty with end doors equals to 3, and the strategy always switch. The strategy always switch. So once we replicate, we put this result to table, and get the proportion prop table. Okay, and we got this result lost in 1. Let me get back to the original screen. So this is the whole function. So we use this package only for this thing. To use pipe operator. Okay, our function and our usage of the function. This is the first usage. The second usage is we are using different strategy, but not always switch, but never switch. And if we never switch, we lose in 0.6 times and 1 only in 0.3. But if we switch, we have this. If we just get rid of our set seat, so no matter how much we try, if we never switch, we will lose in many times.